All right, so this is Unit 1, Kinematics, Lesson 7, Projectile Motion on this worksheet here. So we've gone over the basics of projectile motion in grade 11 that I will quickly review right now. So when we have a projectile, we can split up any projectile into our components, and our components really tell us our types of motion. Right? We have our, at any point, we will have x and y velocities. Okay, and not only that, but for example, gravity also occurs, the acceleration of gravity in our y component. And the great thing about splitting projectile motion up between x and y components is whatever happens in x or whatever happens in y has no effect on the other component. We say they're completely mutually exclusive. So we can consider our x components and our y components completely separate when we're solving the equation. Okay, so let's look at an example. So in our x, we never have acceleration due to gravity. And since we're not going to consider air resistance, the velocity in x remains that way through the entire motion of our projectile. So we're going to have a velocity in x. It'll go a certain distance, which we call the range. So that's our displacement in x. And of course, it'll undergo that distance in a certain amount of time, t. Now in our y velocity, as this undergoes projectile motion, if we just consider the y portion, it goes up, slows down, comes to a stop, comes to a stop at the peak. That's very important. The y component comes to a stop at the peak. That doesn't mean its velocity is 0. It just means the y component of the velocity is 0 at the peak. Okay? So we're going to have an initial velocity and a final velocity. And notice when I labeled initial and final velocity, I chose 2 points. You can choose any 2 points you want. I can call this my initial and this my final. Right? And then my equations will reflect that. For example, if this is a level field, I didn't quite get over there. If this is a level field, and I say this is my initial and that's my final, and my acceleration is acceleration due to gravity, 9.81, you can calculate displacement and it will say displacement is 0. However, if you say this is your initial and this is your final, and then you do your calculations, it will no longer be 0. It'll give you some positive value, which will be, in this case, the point I chose is at the maximum height. So it's going to lead us with some displacement in y due to some acceleration in y over some t, value of time. Now the only variable that is identical on both sides is time. So if you ever have to solve 2 equations for 2 unknowns, which we're going to have to do, time is the great one. Right? That's the one that you can actually solve in one component and substitute into the other. Okay, you cannot solve for Vx here and substitute that for Viy. You can't solve for delta dx and substitute that in for delta dy. They're completely different variables. Okay? All right. So let's try a problem. Now the first problem is just being launched horizontally. But this is going to go over quite a few things that I could ask for in a projectile motion question. And like I said yesterday, when we're solving problems, draw a picture so you can visualize everything that's going on. And that'll help you choose what equations will help you solve the problem. So this says a marble rolls off a table, let's draw a marble, with a velocity of 1.93 meters per second horizontally. So our x velocity is 1.93 meters per second. Since it's launched horizontally, it has no initial velocity in y. So we're going to write Viy is 0. This says the tabletop is 76.5 centimeters above the floor, and it's going to fall like that. So our displacement in y, put it into meters, not centimeters, is 0.76 0.765 meters. And I'm going to write down this, I should write to the right. Okay, now I need to choose a coordinate system. Now obviously it makes sense to choose that as our positive x value, because why would I want to make this and my displacement in x negative? Now for our y value, it kind of makes sense to choose down as positive, because there's no initial velocity up. Acceleration is down. Our displacement in y is down. So just less negatives to worry about. So that's going to be our coordinate system. Just going to erase that so I have room to do the equations. Put it up here. Plus x plus y. Now the first question says, how long the ball is airborne? Okay, so I can attack this problem using y coordinates or x coordinates, or maybe both. Now if I look at x coordinates, you only have one equation you can use in x. It's this. Okay? Because there's no acceleration in x. I mean, you can write the whole equation if you want, which is an equation I find students get very used to, but please do not confuse this for 9.8. This is not 9.8. Since we're writing this equation in the x component, that a would be our acceleration in x. And there is no acceleration in x. I could prove it. Accelerated down, not left or right. So there's no acceleration in x. So this value is actually 0, which means this whole term vanishes. We're only left with that. Okay. Now since that's the only equation we can use in our x component, and it looks like this is the only variable I actually know, there's two unknowns there. Can't really work with it. So let's look at the y equation. Now in our y components, we have 5 equations for uniform acceleration. Now, in order to solve for anything, we need 3 pieces of information. And it looks like we have 3 pieces of information. This is 1, this is 2, and our third one is, of course, acceleration due to gravity. So I can use this equation to solve for part A. Our displacement in y is VIY delta t plus 1/2 AY delta t squared. Okay, VIY is 0, so this whole term is just going to disappear. And then we can rearrange to solve for time. The square root of 2 delta dy over ay. Okay, and we know what delta dy and ay are right here. And of course ay is 9.81 meters per second squared. Why am I not making gravity negative? Because I chose down to be positive. Right? Gravity isn't always immediately negative. You decide what direction is going to be positive and what direction is going to be negative. And then you need to stay consistent with that throughout the whole problem. Don't change it halfway through. All right? So we plug in those values and you'll get 0.395 seconds. So there's part A. Now part B says what's the range, the horizontal range? Well, now that we know time, we're going to solve for range. We go back to this equation. Before we only knew velocity. Well, now we know time as well. Because remember, time is the same in both coordinates. Okay? It doesn't make sense that it would be different, because then the ball that's flying would split up into 2 balls traveling to different coordinates at different times. It doesn't make sense. Time is the same. Right? So here we're going to have, we substitute 0.395 and our x velocity 1.93, and we get a range of 0.762. Okay, that's probably the easiest question right there. Now the next question, part C, usually if I have this question on a test, students usually only answer half the question and then they stop because they think they're finished. So I'm going to answer this question, and I want you to think about when I'm actually finished the question. I'll make a couple pauses and we'll see if you think I should keep going. So it says the velocity at impact. So I want to know the velocity right there. All right, well, since I know many components in y already, I can simply write our final velocity equals our initial velocity plus a delta t. Initial velocity we know is 0, so it's just a delta t. When we solve for time, I wrote it here somewhere, I think it was 0.395 seconds, and we have acceleration 9.81, so we multiply those and we get 3.87 meters per second. Am I done? It says the velocity at impact. Didn't I just do that? No, I didn't. And here's why. Okay, this equation is being done in what component, x or y? It's being done in y. So these are all of our y components. So what I solved for is the y component of that velocity at impact, not the actual velocity at impact, just its y component. So I'm not finished the question. Now the x component I know. It's the same as the initial velocity in x, or I can just write vx, because there's no acceleration in x. So that's 1.93 meters per second. So if I were to sort of write this vector, which is vf, and split it into x and y components, this is our x at 1.93, and this is our y at 3.87. What I need to solve for is that hypotenuse. That's what the question is asking. Now doing that is not hard. It's Pythagoras, and then of course you need to know the angle too, because velocity is a vector. So it's not hard. You've been doing Pythagoras since grade 10 math. And simple SOHCAHTOA, you've been doing grade 10 math as well. So you've been doing it for a long time. It's just the understanding that you're not finished the question here. It's understanding components, what they mean, and how they're different from the actual vector, in this case for final velocity. All right, so let's solve for the magnitude of that final velocity. Take the square root of 1.93 squared plus 3.87 squared, and we get 4.32. So there's our final, well, magnitude of our final velocity anyways. But now we need to solve for the angle. So tan theta was opposite over adjacent. So 3.87 over 1.93. And we can solve for theta to be 63 degrees. All right. Now here's another mistake I see people make. So let me just erase this. They'll write their final. They'll say final velocity is, what was it, 4.32 meters per second. And then that 63 degrees, they'll write like this. Well, that's east 63 degrees south. And that is wrong. Why is it wrong? It looks like it's right. Well, it looks like it's right because I've written it on a two-dimensional plane. But when you think of it in the real world, when you throw something, it does this. Is that downwards direction south? No. South would be horizontal. East would also be horizontal, right? North would be horizontal. They're not pointing downwards. So it doesn't make sense to say this. That means the projectile looks like this. And it's not actually falling. So how are we going to write this? Well, what we usually do is we'll write it as 63 degrees. Now, I solved for this angle instead of, say, I could have easily done this, write my components like this, and solve for this angle. But instead, I solved for this one. And the reason I did that is because that's the angle below the horizontal. And so I can simply say 63 degrees below the horizontal. I know it's a lot more to right than east and south, but that's the proper way of doing it. All right, so let's look at question 2. Question 2, I'm going to get you started, but again, I made a whiteboard animation video for this one, so I want you to get started on it. It's not too much of a jump from question 1, but I'm going to get you started on it. Now, the big difference with this question, right, is we throw it at an angle, like this. Now, because it's being thrown at an angle, the initial velocity in y is not 0. Instead, we have some non-zero value for our y, initial velocity in y. This is our velocity initial. So that means when we plug it into our equation, well, let's look at our y component equation. Delta dy equals viy delta t plus a half a delta t squared. Now in grade 11, most questions that you got were either thrown horizontally, which means this whole term is 0, and you can solve for time just like we did, or they were thrown at an angle on a level plane, which means this was 0, okay? And then you can cancel out 1 delta t in each term and solve for t that way. In this case, viy is not 0. Also, delta dy is not 0 because we have some downwards displacement. So you're going to have to solve for time using the quadratic formula. Okay, so that's a big difference there. But that's the only extension we really need to do. So try that. Draw a picture of it, write all your given information down, solve for your components. Okay? And then once you have your components, because the question doesn't give you their components, the question just says 12 meters per second, so this is 12, 42 degrees above the horizontal, so that's 42 degrees. So you will have to use your trig ratios to solve for this and solve for that. Once you do that, you can go ahead and use your equations of motion in y and in x. Okay, so try it. If you get stuck, watch the whiteboard animation video. But what I want to do now is look at another problem. Just going to make this a little smaller. All right, so here's the problem. This is going to be like a golfing problem. Now this is going to be completely level, and we're trying to get a hole in one. If it's completely level, one thing that we know is our displacement in y is going to be 0. Displacement in x, it looks like it's exactly 300 meters. The reason why displacement in y is 0 is because it starts and finishes at the exact same height. Okay, what else do we know? We're going to launch it at some angle and at some initial velocity so that we perfectly get a hole in one. Now to make things easier, I can say we're going to launch it at 45 degrees. Why 45 degrees? You might remember in grade 11 we talked about 45 degree being the optimal angle to get the maximum range for a projectile. Okay, and I'm going to prove that to you right now while solving this problem. But I want you to try the problem too. So here's the problem. What initial velocity do we need to set this to? And I can set it to whatever you like. What initial velocity do we need to set this to for an angle of 45 degrees to get a hole in one? All right. So here's how we're going to do this. Here's our initial velocity. Okay, we don't know what that is. Here's our angle theta. Let's assume we don't know what that is. Now, usually the first step when we're solving a projectile question is to actually, let me make this bigger, find the components. And in this case, you can't find the components, so I sort of see a lot of students get stuck and they stop. Why did they stop? Because they can't get a number for these sides. Don't worry about getting numbers. You can still solve for the sides without the numbers. You can just find an expression for them. Right? Letters are more important than numbers. They tell you so much more. So let's write them. So Vx is actually Vi cos theta. And Vy is actually Vi sin theta. There you go. We solved for the components. Okay, let's look at our x equation. We have delta dx equals Vx times time. Okay, well, Vx we've solved for. It's Vi cos theta times time. This we know is 300, but we don't know any of these. So we're stuck there. Leave it. Don't erase it. It's good work. Okay, but you need to try another approach. So let's go into our y component. Now our y component looks like this. Delta dy equals VIy delta t plus 1/2 a delta t squared. Now what's a? Well, acceleration, right, is, I'm going to make up positive. So acceleration is actually minus 9.81 meters per second. But because I just want to play with letters, I'm just going to say it's equal to minus g, where g is our magnitude, 9.81. So I'm going to do some subbing in here. VIy, you know, is Vi sine theta times delta t. And then I'm going to substitute a negative g for a. So minus 1/2 g delta t squared. All right. So it kind of looks like I'm almost stuck there as well, except I do know delta dy is 0. So let's put a 0 in for that. Now because I have a 0 there, and because I know time is not 0, I can divide every term by time. If there's a possibility that some variable could be 0, you shouldn't divide through by that variable. Okay? All right, so rearranging a little bit here, I can have Vi sine theta equal to 1/2 g times delta t. And it seems like I'm stuck again. But what did we do in the previous question? Just even the simple horizontal marble rolling off a table. Well, we solved for time in one equation and substituted in the other. But we did it with numbers. Well, how is this any different? We can still solve for time in one and substitute it in the other. We just won't use numbers. We're going to do the same steps though. So let's try that. Here, if I solve for delta t, we get delta dx over Vi cos theta. So let's take that and substitute it in for time over here. So here we have Vi sine theta equals 1/2 g all times by delta dx divided by Vi cos theta. Okay, it's running out of room here, so I'm just going to erase this. Now I'm going to take this and I'm going to rearrange, and I'm going to show you the range equation, which you may or may not remember from grade 11. So I'm going to solve for delta dx. Now if I do that, right, I'm going to bring this 2 Vi cos theta on the denominator up here, and I will get 2 Vi squared sine theta cos theta all over g. All right. Now, actually, I'm going to write the 2 and the Vi in a different order, and I'll show you why. Let's write Vi squared. I'm going to put a 2 there. I'm going to put brackets around there. Does that bracket ring any bells for you? Probably did it in grade 11 math. It's a trig identity. It's a double angle one. It might be grade 12 math, I can't remember. I think it's grade 11. So we get Vi squared over g times the sine of 2 theta. Now you don't have to use that identity. You can easily just I told you theta is going to be 45 degrees, and you can just plug it in, use your calculator. But if you try to simplify an equation more, it tells you something about the world, as opposed to just punching numbers into a calculator. And in this case, look what it tells you. If we want to maximize range, well, we could hit it harder, but let's say we want to maximize range for some value of initial velocity on planet Earth. But we can change the angle at which we hit it as. That means to maximize range, this needs to be as large as possible. Well, the sine of some angle, the largest value it can be is 1. Okay, so let's force that to be 1 in order to maximize range. So the sine of 2 theta, we want to be 1. All right. Well, what does that mean? That means what the sine of what equals 1? 90, right? Sine of 90 degrees equals 1. So that means 2 theta must be equal to 90 degrees. And therefore, theta must be 45 degrees. So that's mathematical proof that to maximize range, you need to hit at an angle of 45 degrees. Now in this question, you're hitting at 45 degrees. That means this is going to be 1. And I asked you to solve for initial velocity. So in this case, initial velocity is just the square root of delta dx times g, or the square root of 300 times 9.81, which is, I lost my calculator. I think it's 45.2. Let's try it. So if I change this to 45.2, hit the ball. No, it's not. I need my calculator. Hold on. I'm going to pause this. All right, so I got my calculator. So the square root of 300 times 9.81 is 54.3. I got my numbers mixed up. All right, so let's reset this. And let's do 54.3 and play. All right, great. We're good. I'll see you at the next lesson.